Okay, class, we are back again to discuss a little bit more about similar figures. You saw in our activity in class a brief introduction to the idea of similarity with the similar rectangles. We want to expand that a little bit now to talk about similar figures as a whole, and in specifics then to go into the idea of similar triangles, kind of like we did earlier in the year with congruent triangles. So let's jump right into it. In similar polygons, two polygons are similar if their corresponding angles are congruent and their corresponding side lengths are proportional. This is the definition I would have written down somewhere, preferably your composition book, so you can look back in it. So again, they are similar if corresponding angles are congruent and corresponding side lengths are proportional. So if we were to look, for example, at these two polygons right here. In this polygon, it's telling us that ABCD, that polygon, is similar to EFGH, and that symbol in the middle is just that little tilde squiggly line, like we did before. When we did congruence, we had a symbol that looked like that for congruence figures. We're now no longer doing congruence, just similar, so we get rid of that equal sign. So in this one, both of these figures are congruent to each other. That means we can point out a couple of key things. Each of these angles, the corresponding angles, must be congruent. So A and E must be congruent. We can go through and say that B and F are congruent. We can go and say that G and C are congruent. And we can finish it off by saying that angle D and angle H must be congruent. Just from that that similarity statement, we can say those four angles, corresponding angles, must be congruent. Now, in congruent figures, we are then able to say that if we went through, for example, that first segment AB and that segment EF had to be congruent to each other. Well, we've seen here with similarity already that we're not talking about the lengths being exactly equal. All we need to have is those lengths be proportional. So in this case, AB and EF would make a ratio. It has to have the exact same ratio as the next segment, which would be, in this case, BC and FG. So you'd have to have the exact same ratio as a result. And you can go right down the line for the other segments as well. And remember, with our proportion rules, you could have also set this up in another way. Instead of AB over EF, you could have said AB over BC would have to be equal to EF over FG. Just a different way. We'll be seeing different ways that we can set up these ratios, these proportions, as we're going through. But the main thing is all the ratios of corresponding sides must end up being proportional. No longer dealing with having to be completely congruent, but just proportional, that we can put it in this ratio. So let's look at an example of what we can do. In this diagram here, we have that these triangles are similar to each other. Now, because of that, again, we can immediately read off a few things immediately. The first thing is with the congruent angles. Just like we did in congruent statements, we can do with the similarity statements. We can immediately say that angle R must be congruent to angle X. We can also say angle S is congruent to angle Y, and we can also say angle T congruent to angle Z. And that's just straight from our statement here. R is to X, S is to Y, T is to Z. So that's part A. We're good. Part B. Check that the ratios of corresponding side lengths are equal. So if we look through, we would want to look at RS versus XY. RS is 20, XY is 12. So that's our first fraction, our first ratio. Our second one, ST and YZ. ST is 30, YZ is 18. And in our last one, RT, XZ. RT is 25, XZ is 15. Now, you can find all three of these fractions. If this is a true statement, then we do have the ratios being equal to each other. Let's take a look at them. If we reduced this fraction, you could factor out a 4 from both of these, and you would have a 5 over 3. In the second one, if you factored out a 6, you would have 5 over 3. And as you can probably guess for this last one, factoring out a 5, you would get 5 over 3. So all ratios are equal to each other. that means that these, by the side lengths are proportional, so we're one step closer. We do now have similarity, we do have similar triangles because angles are congruent, the sides make up proportionals, they have equal ratios. Alright, and in this last one, write the ratios as a statement of proportionality. That is this statement right here. When you put each of those into a proportion and set them all equal to each other, this is an extended proportion because we now have three things that are all equal to each other. But you set it up, rs over xy is right here, 20 over 12, st over yz, 30 over 18, and rt over xz, 25 over 15. So that right there is part C. Alright, we have one last thing we want to look at, and again, it's just if we're given this statement to begin with, can we write all the angles and can we write the ratios? So let's do it again. The angles would have to be angle J congruent to angle P, angle K congruent to angle Q, and finally angle L congruent to angle R. Same exact way again as when we did congruent figures, we just bring it over to similarity. Now, in terms of the ratios, we want to do first those first two segments. We're not saying they're congruent anymore. We're saying that if we put them into a fraction, jk over pq, that is going to be the same ratio as the next two, which would be, in this case, kl and qr equals to kl over qr. And our last one would be what's remaining left, which would be jl over PR. And that's from JL and PR. So that is what we mean by we want a statement of proportionality with the ratios, and again, your angles that were already there. Okay, let's move forward at this point and see what else we know. Scale factor is an idea that we're going to hear a lot of. In the previous problem, actually, let's go back to that real quick. In this previous problem, when we reduced all these fractions, we ended up with this number of 5/3. That was our common number when we had those ratios of the corresponding lengths. All those ratios were actually equal to each other. That ratio is known as the scale factor. It is what you would have to multiply one of the figures by to get the length of the other figure. Again, these similar figures are essentially just an enlargement of another figure you know. So, for example, if we had if we just had a triangle here, that was one triangle, we could say have another triangle the exact same. We just decide to make it a little bit bigger. It's just an enlargement. This is where we're getting our idea of similarity. And the scale factor is how much you would multiply this first smaller triangle by to get to the larger triangle. Scale factor is just the ratio of the sides, how much you need to enlarge it to get from one figure to another. So let's take a look at how we're going to work with that. In this diagram, we have, again, some similar figures. We want to see what the scale factor is. The easiest way to look at that is to set up these proportions. And then when you do, AB over QR would become 12 over 6, which you should immediately know when you reduce that it should be 2. Check another one. If you do BC over RS, well, BC you don't know. BC over RS is x over 4. CD over ST, CD is 16, ST is 8, which is also a ratio of 2. So your scale factor is 2. You have to have a 2-to-1 correspondence here. Twice as big is this first segment ABC, or is this first polygon ABCD as QRST is. So when we have this now, we also were going to ask, how can we find this missing value here of x? Well, all we need to do is just set up the proportion. If you wanted to, you could go with AB over QR equals BC over RS. When you plug those in, 12 over 6 equals x over 4. You can do your cross multiplying, and you would find that x equals 8 as a result. But again, we should have known that just by looking at the scale factor. If all these segments in ABCD are twice as long as QRST, that means that you would take RS, because RS and BC are the corresponding sides in these similar figures. You would take 4, multiply it by 2, you would get 8. That's what x has to be. And that's why you get an answer of 8 there for x. Alright, One final thing we want to talk about is the perimeter of these similar polygons. Now, as we saw when we were doing the idea of the mid-segment, if we had a triangle here and we knew the outside of this triangle, if we knew that the sides of the big triangle were 6, 10, and 12, we were then able to go and say we knew what these inside triangle, or I'm sorry, yeah, these inside segments, these mid-segments had to be. They were just cut in half. So 6 was half of 12, 5 half of 10, and 3 half of 6. When we did that, we realized that, okay, the perimeter of this outside triangle had to be twice the perimeter of the inside triangle. Well, this is actually this is true because of the mid-segment theorem, but it's also because these two triangles actually are similar to each other. If we were to take this inside triangle right here, if we were to just rotate it so we can see a little bit better what we're looking at here, all we have is a 2-to-1 idea of similarity here, because each segment of this smaller triangle is exactly half the length of the big triangle. So essentially we have two similar triangles here, and all the ratios line up. You would have as ratios 10 over 5 is equal to 12 over 6, which is equal to 6 over 3. So really, in these mid-segment triangles that we were doing in the last unit, we were actually dealing with a special case of similar triangles. This just had a scale factor of 2. And as we saw when we did the perimeters, the perimeter was all based on the ratio of the side lengths. So if we knew the perimeter of the outside triangle, we knew the inside triangle based just upon what the scale factor was. And in this case, the scale factor was 1/2, meaning that if the outside perimeter was, in this case, 10 plus 6 plus 12, which is a grand total of 28, that means that the inside triangle had to be exactly half of that, because it had to be the same as our scale factor. So we can say the perimeter of the big triangle had to go along with the perimeter of the little triangle. And because of that, in this case, our answer was 14. Now we don't have to do that just for triangles, we don't have to do it just for mid-segments, we can do it with any similar polygons. So this here is another theorem that I would have written down into your composition book to be able to look back upon, and just to say that we can always find what the perimeter is. So let's do a quick example with this problem, and then we will wrap up this video. If I have, say, this triangle here versus a second triangle, if we say that they are similar, let's call this one triangle ABC, and we'll call this triangle over here DEF. So we'll call this ABC and triangle DEF. And we know that these triangles are similar to each other, and we want to find the perimeter of it. Let's say, for example, all I need to know is that if we know this is 9, if we know this is 10, and this is 12. Let's say I also know that DE is, we'll say 3. If DE is 3 and AB is 9, we can already set up a proportion that we can work with. We know we can find the scale factor immediately. The scale factor is based on the corresponding parts. AB and DE are the corresponding parts. So 9 divided by 3, which reduces to just 3. That means that the perimeter of triangle ABC over the perimeter of triangle DEF, and this is straight from the theorem that we just saw, that has to follow the same scale factor of 9 over 3. You can do cross multiplying to find this. We know that the perimeter of triangle ABC from looking at the picture is 31. We can plug that right in, and you can go and cross multiply. When you do that, you would get 93 equals 9 times that perimeter of triangle DEF. And then you would just simplify from there, and when you do, you would get it would be 10 and 1/3 would be the perimeter of triangle DEF. And you can again do that just by using the fact that the perimeter has to have the exact same ratio, the exact same proportion as what the scale factor of the two triangles is. Well, that is all we have to deal with in this section. we will continue moving on with this here in the next couple of classes, both in class and then here again online. Make sure you take the quiz. Do not forget to take the quiz at the end of this. And when you come in on Monday, you should be in good shape to begin working on this new unit dealing with similarity. So again, remember the quiz, and we will see you guys later.